An atom measures a minuscule 0.1 nanometers across. Because they are so unfathomably small, up until just 30 years ago, directly seeing one was considered physically impossible. This diagram illustrates the roadblock of visible light. At 380 to 750 nanometers, it's over 3,000 times larger than an atom. Instead of reflecting, light simply diffracts around it, like trying to measure a grain of sand with a skyscraper-sized ruler. The solution came from a 1924 breakthrough by physicist Louis de Broglie, who proved that matter has a wavelength too. By accelerating electrons to 80% the speed of light, you compress their wavelength to roughly 2 picometers, 100,000 times smaller than visible light. Electrons had the raw resolving power to clear the light barrier. We had our illumination source. The new problem was how to actually focus it. You cannot focus an electron beam using traditional curved glass. The particles will just hit the glass and stop. In the late 1920s, a young PhD student named Ernst Ruska found a workaround. If electrons couldn't be bent by glass, he would steer them using electromagnetic fields. Ruska built what became known as a magnetic lens. By coiling wire around an iron core and leaving a gap in the middle, passing a current through the wire induces a donut-shaped magnetic field across that gap. When high-speed electrons approach this gap, the magnetic field exerts a force on them. This Lorentz force kicks in, pushing the particles into a tight, spiraling circular motion. As the electrons travel along the inside of that donut shape, the circular motion forces the entire outer rim of the beam inward. Every electron is steered directly into the center, converging them to a single focal point. This invention became the transmission electron microscope, or TM. It successfully shattered the glass barrier, giving researchers the ability to magnify specimens more than 10,000 times. Engineers had built a functional lens out of thin air and magnetism. But this mechanical triumph was about to crash directly into a fundamental mathematical law. Just as the TEM was gaining momentum in 1936, a physicist named Otto Scherzer published a devastating paper detailing a flaw in the microscope that he proved was completely unavoidable. This graph maps how electrons deflect based on their distance from the center. The magnetic field of Ruska's lens doesn't scale linearly. It pulls much harder at the outer edges. Electrons further from the center get over-deflected, focusing much too early and missing the central point. This creates a blur across the image known as spherical aberration. In standard optical cameras, you fix this blur easily. You take your converging lens and you pair it with a diverging concave lens that pushes light outward. The two equal but opposite errors cancel each other out. But magnetic fields follow Maxwell's equations. Every field must start at a north pole and end at a south pole, forming a closed loop. Because of this geometry, any perfectly round, radially symmetric magnetic lens will always pull electrons inward. It is physically incapable of pushing them apart. Mathematics strictly forbid the diverging lens required to fix the blur. With no way around Scherzer's proof, the resolution of deep atomic microscopy was stuck for the next 6 decades. In the 1990s, 3 scientists, Knut Urban, Max Heider, and Harold Rose, decided to target a specific loophole in Scherzer's proof. His math only applied to lenses that were perfectly round. To get around the law, they had to break the symmetry entirely. They designed a highly complex piece of hardware called a hexapole. Instead of a smooth, uniform ring, this uses a nest of 6 separate electromagnets to generate a chaotic, bumpy inner field. When the flat, circular electron beam passes through this hexapole, the asymmetrical field violently twists and warps the beam into a triangular saddle shape. By destroying the image this way, they created a highly deformed shape that features a slight concave bow right in the center. That bow forces the electrons to diverge, just a tiny bit. The team then forced this deformed beam through a second inverted hexapole. This unbends the saddle back into a flat circle, but manages to successfully retain that tiny diverging effect in the center, exactly what they needed to cancel out the spherical blur. By deliberately tearing the beam apart with chaotic fields, they engineered a mathematical backdoor around the laws of physics to achieve perfect focus. In July 1997, the team had only days left before their final sponsor pulled their funding. They placed their newest, untested lens into the microscope, let the massive magnet settle for 24 hours, and powered it up. The picture stabilized. The spherical aberration vanished completely. By correcting the blur, they successfully drove the microscope to a resolution of just 0.13 nanometers. After over 60 years of failed attempts, scientists could finally look directly at crisp, unmistakable images of individual atoms. Today, aberration correction is standard equipment in modern laboratories. Researchers rely on it daily to observe exactly how atoms arrange themselves, driving modern chemical engineering and material science forward. Sometimes, seeing further requires deliberately breaking the perfect symmetries we built our theories on. An idea declared mathematically impossible in 1936 is now the tool we use to map the atomic foundation of our world.